started. I do have a lot to cover today. So I'll just do a quick introduction of myself. I'm both the usual introducer for these and moderator for these, and also today's speaker. So I'll just do a quick intro of myself. So I'm Rachel Nethery. I'm an associate professor in the biostatistics department at the Harvard School of Public Health. I'm also an internal cafe team member working on capacity building. And today I'm going to be talking to you guys about quasi-experimental causal inference methods for health and extreme weather research. And just a logistical note before we get started. I don't think you'll be able to unmute yourself or anything during this webinar. But if you have questions as we go along, please put them in the chat and we'll try to leave a little bit of time at the end to address any questions, or if there's something urgent that comes up in the Q&A box, Elaine from the cafe team can interrupt me and let me know. Otherwise, I'll do a few Q&As at the very end of the talk. So let's get started thinking about the motivating question. So let's imagine that we want to estimate the health impact of some extreme weather event. So let's think about, just to make life simple and concrete, let's say that we want to investigate the impact of a particular major hurricane on mortality in the counties that were affected by the hurricane. Let's think about how you might start out if you wanted to investigate this type of question. Your first thought might be, can we just compare mortality in the hurricane exposed areas before and after the hurricane? And the answer is yes, you could, but particularly if you're in settings where you're looking at sort of effects that might drag out over a long time period after the hurricane. This can be tricky because you might end up conflating sort of secular time trends in mortality with effects of the hurricane. So just comparing before and after hurricane isn't always ideal. You might then think, what if we just compare mortality in the post-hurricane period in hurricane exposed versus control counties, so comparing to places that weren't exposed to the hurricane. This also isn't ideal because there might be a lot of factors other than the hurricane exposure that differ in exposed and unexposed areas. And you might think, well, maybe I can measure a lot of those factors and adjust for them in this analysis. But that can be tricky to do, and you never really know if you've sort of captured all of those confounding factors that might differ between exposed and unexposed areas. And so quasi-experimental approaches to answering these types of questions at a high level can help us mitigate some of these sources of bias. So first off, what is a quasi-experimental study or a quasi-experimental design? In general, it's just kind of a term that's used to describe a study design that's focused on estimating effects of a policy or intervention or exposure in a context where you weren't able to do randomization to exposure status. So to be consistent with the general causal inference literature, we're going to refer to the policy or intervention or exposure that we're interested in generically as the treatment. So in our context, that treatment would typically be a exposure to an extreme weather event. And in these quasi-experimental designs, not exclusively, but most of the time, treatment status is assumed to be binary or at least discrete. So you're either treated or you're untreated. And so these quasi-experimental designs, again, are trying to estimate causal effects in the absence of a randomized design. And so similar to observational studies, they're going to try to leverage naturally occurring variation in treatment status across sort of pre-treatment and post-treatment time points and across exposed and or treated and untreated areas to estimate what would have happened in the absence of treatment. But unlike sort of traditional observational study designs, these quasi-experimental designs are particularly powerful because they can adjust for certain types of unmeasured confounding by design under the kind of canonical assumptions of the methods. So we'll talk more about what that means coming up. And so I wanted to talk about this topic today because I've noticed that these quasi-experimental designs are increasingly being used to estimate health impacts of extreme weather events in the literature, primarily things like hurricanes, floods, and heat waves that are kind of like these big discrete events. These quasi-experimental designs are not as well suited for estimating effects of exposures that are kind of continuously varying over time, like air pollution or temperature. So really going to be focused today on thinking about extreme weather events that are kind of these big discrete things rather than day-to-day variability in an exposure. And a lot of quasi-experimental approaches rely on panel data, and actually all the methods we'll talk about today assume that we have panel data. And panel data here just refers to sort of observations of our outcome of interest. In our motivating example, that was mortality. In treated and control units, across multiple sort of common time periods, and at least one of the time periods at which you observe both treated and control units should be before treatment, and at least one should be after. So you have some pre-treatment and some post-treatment time periods. So the units in panel data structure are typically things like spatial areas, like counties or zip codes or states. And when we talk about the units of our analysis, we'll be thinking about generically one of those types of spatial areas, and we'll be indexing units in the sort of modeling frameworks using the I index. Our times could of course be sort of any sort of grouping of time, days, months, years, whatever is appropriate, and we'll sort of denote or index the time periods over which we've observed the units in the data using the T subscript. And we're going to assume for the purposes of today's discussion that treatment began at some known time during follow-up, T0, and that sort of, we'll generally assume that sort of timing of treatment initiation is common across all the units that receive the treatment, so all the treated units, and that treatment is what's called an absorbing state, meaning once a unit is treated, we assume that it never goes back to being untreated during the follow-up period that's captured in our panel data. And then we're going to let YIT just denote the outcome that we observe in unit I at time T. So this slide's a little bit notationally heavy. I am going to introduce potential outcomes, which are kind of fundamental to causal inference, conceptually to causal inference. But then I promise the whole rest of the notes won't be so sort of notationally intense. So we're going to define potential outcomes using this superscript and parentheses notation. So this YI post 1 is what we'll call the potential outcome under treatment, and it represents the outcome that some treated unit I would experience in a post-treatment period with the treatment. And so this potential outcome is, of course, what we always observe. In post-treatment periods, treated units we observe their outcomes with the treatment. So this YI post 1 is a quantity that we observe. This YI0 is going to be, we'll think about it as the potential outcome under control. And it's just the outcome that would be observed in treated unit I at a post-treatment time period had the treatment not occurred. And so this potential outcome under control is, of course, never observed. We never observe what would have happened in a treated unit in a post-treatment period had the treatment not happened. And so this potential outcome is referred to as the quote-unquote counterfactual outcome. And so the fundamental, what's called the fundamental problem of causal inference, is that we want to compute a treatment effect, which is just the difference in the potential outcome, the outcome that would have occurred under treatment and the outcome that would have occurred under control in the post-treatment period in treated units. But the problem is that for treated units post-treatment, we always observe this potential outcome under treatment, and we never observe this potential outcome under control. or the counterfactual. So the task of these quasi-experimental methods for panel data is to try to estimate the counterfactual outcome. So the outcome that would have occurred in treated units absent treatment in the post-treatment period. And so we're going to see that there are several different sort of approaches to quasi-experimental analysis, study analysis, and they all kind of make different assumptions to enable estimation of these counterfactual outcomes. So we're going to talk about what I would say are the two most popular methods for quasi-experimental analysis, which are difference in differences, or DID, and the synthetic control method, or SCM. So we're going to talk about both of those in some detail today if we have time, and then we'll just briefly touch on some modern generalizations and extensions of these methods that might be more practical for real data settings. And throughout this talk, we're going to be coming back repeatedly to a running example of trying to estimate hurricane health impacts. So again, supposing we want to estimate the effect of a major hurricane on mortality in counties that were exposed to the hurricane. And we're going to assume that we have, for a whole bunch of counties, we have a binary indicator of whether the county was exposed to a hurricane or not. And we have time series of mortality for each county covering both some pre-hurricane and some post-hurricane time. And if you're interested, we're not going to talk about how you actually measure hurricane exposure here today, but if you're interested in that, we actually did a previous cafe webinar on how to measure hurricane exposure, and the link is here, and we will sort of post these slides when we post the video, so you'll be able to click the link in the slides later when we post them. So again, we're going to be assuming that in these hurricane exposed areas, we have some observed death counts in the pre-hurricane and post-hurricane period, and we're going to be trying to estimate the counterfactual, meaning how many deaths we would have observed absent the hurricane in the post-hurricane period. So we're going to be trying to estimate this green line here. And so we're first going to talk about difference in differences, which I think is by far the most commonly used quasi-experimental method, and kind of usually the first that people are introduced to. So in the sort of canonical DID difference in differences setup, we assume that we have what's called a 2x2 data structure, meaning that we have outcome data measured from two treatment groups, the treated group and the control group, for just two time periods, one pre-treatment time period and one post-treatment time period. So this is what's referred to as the 2x2 case, or the 2x2 data structure for difference in differences. We are going to discuss how you can generalize difference in differences beyond this simple setup, this 2x2 setting, but it's easiest to sort of grasp the concepts when I'm introducing it in the 2x2 setting. So we'll first introduce the concepts there. So we're going to be assuming that our data have this kind of structure where we have units, we have some kind of unit identifier in our data. And for each unit, again, in the 2x2 case, we observe them at two time points, one pre-treatment time point and one post-treatment time point. So here we're assuming that sort of October 1 is the treatment time, and so September is our pre-treatment time point, and October is our post-treatment time point. And then for each of these units and time points, we observe an outcome. And then we're going to assume that our data have these two columns that we'll call treated and post, where treated is just a binary indicator of whether this particular unit in this row was ever treated. So for unit 001, it was treated in the post-treatment time period, so it has a 1 in its corresponding rows. And then we're going to have this post column, which just tells us if the time period represented by this row is a pre-treatment or a post-treatment time period. And so the key idea behind DID that allows us to estimate counterfactuals and thereby treatment effects in this context is what's called the parallel trends assumption. So the parallel trends assumption says that in the absence of treatment, on average, outcomes in treated and control units would have evolved in parallel over time. And so you're seeing kind of an example of this in the plot here. So we're seeing sort of the dots are pre-treatment and post-treatment outcome average outcomes in the treated and control units. So the control units are in the blue and the treated units are in the orange. And then the parallel trends assumption tells us how to estimate the counterfactual in this context. So how to estimate what would have happened in the treated units in the post-treatment period absent treatment. It tells us, the parallel trends assumption tells us that absent treatment, the lines in the treated and control units would have been parallel. So absent treatment, the treated units average outcome in the post-treatment period would have been here. It would have followed this line parallel to the control line. So then once we have that estimate of our counterfactual outcome, the treatment effect is just the difference in the outcome that we observed with the treatment at the post-treatment time points and that counterfactual, what would have happened absent the treatment. And so the nice thing about difference in differences is that unlike those little sort of toy examples of possible analytic approaches that we talked about at the very beginning of the talk, with difference in differences, thanks to this parallel trends assumption, we don't need to assume that treated and control counties or treated and control units are directly comparable. We also don't need to assume that pre and post-treatment times are directly comparable. We just need to assume that treated and control units would have stayed as different as they were in the pre-treatment period into the post-treatment period had the treatment not happened. So we need to assume that they would have stayed as different as they were here at the pre-treatment time, at the post-treatment time in the absence of treatment. So why is this approach called difference in differences? Well, to understand that, it's helpful to kind of think about how we estimate treatment effects in this setting. So our treatment effect, which in this slide we're going to start calling delta, we estimate it as the difference represented in this purple line here. So this gap between the treated, the observed outcome in the treated units post-treatment and the counterfactual is our treatment effect estimate. So you'll notice that this purple line, this purple gap here can be computed by first just taking the difference in the treated and control unit outcomes post-treatment, which you see in the red here, and then subtracting off the difference in the treated and control units outcomes in the pre-treatment period. And so the difference in those two quantities gives us this purple quantity here, the treatment effect estimate delta hat. And so this is called difference in differences because in this simple 2x2 setting, the way that we estimate the treatment effect is actually just by taking a difference in two differences. In practice, though, we typically these days don't actually do our difference in differences analysis using this sort of simple averaging approach. Instead, in order to sort of be able to better facilitate inference, we usually take an equivalent approach that actually specifies a regression model to do the estimation of the treatment effects. And you get the exact same treatment effect estimate in the 2x2 case from this regression model as you would from actually taking the difference in the differences. But you can also easily get uncertainties and things like that, confidence intervals and p-values and whatnot that are a little bit more conceptually difficult to get in the sort of simple difference in difference quantity setting. So the regression model that you specify to sort of estimate this equivalent quantity, this treatment effect estimate in difference in differences, just takes your outcomes and models them as a function of an intercept of that treated indicator variable. So remember, if we go back to our data structure here, we have this treated indicator variable, and we have this post indicator variable. So we have an intercept. We have a term for this treated indicator, a term in the model for our pre or post treatment indicator, and then their interaction term. And the coefficient on that interaction term is what corresponds to our treatment effect. So our estimate of the treatment effect delta hat is delta hat. And you can, might not be immediately clear why this delta hat that you would get from estimating the regression model corresponds exactly to the difference in differences quantity that we showed on the previous slide. But I've sort of provided a little graphic here showing how each of the quantities from the previous slide maps to parameters in this regression model. And so ultimately, our delta hat from this regression model ends up being exactly the same as the delta hat that we estimate just by actually taking the simple difference in differences. One reason that we like to use the regression modeling approach for estimation is, like I said, to facilitate inference. Another reason is that when we use a regression model, we can actually also adjust for covariates. So let's assume we have some measured time varying covariates, X. We can also adjust for those in this regression model. We don't need to actually adjust for covariates whose values don't change over time in differences, because those quote unquote time invariant covariates are adjusted for sort of by design in the parallel trends assumption. So remember, the parallel trends assumption allows for pre-treatment baseline differences in the treated and control counties, as long as but it just assumes that those baseline differences wouldn't have changed over time. So that parallel trends assumption that allows for the pre-treatment differences in treated and control counties is kind of by design accounting for any factors, any confounders that don't vary over time. So far we've just talked about the 2x2 setting, but realistically, a lot of times these days we have data spanning more than 2 time periods. And if that's the case, there's a fairly straightforward extension of difference in differences to accommodate multiple pre-treatment and or post-treatment time periods. So more than 2 total time periods. And this sort of extension or generalization of difference in differences is often referred to as the quote unquote 2-way fixed effects model. And so this model is specified sort of similarly to the regression model on the previous slide, but again, allowing for more than two time periods in your data. So here we're modeling the outcome at each unit in time as a function of unit specific fixed effects, which account for time invariant differences across units. Time fixed effects, which account for common temporal patterns across units. And then we have this term delta times this D variable. And so D here is an indicator of whether unit I is treated at time T or not. And like before, this delta quantity is our sort of treatment effect or treatment of interest, treatment effect of interest, and so our estimate of delta will be our treatment effect estimate. And again, like in the 2x2 regression, the 2x2 difference in differences regression model, we can adjust for time varying covariates through this X term. So it's a little bit harder to see from this representation how the 2-way fixed effects model is relying on the parallel trends assumption, but it is just like in the 2x2 DID setting. Here we're still relying on the parallel trends assumption. We're assuming that in the absence of treatment, treated and control units would have sort of evolved, their outcomes would have evolved in parallel. And so the way that that's kind of being imposed in this two-way fixed effects model is through these sort of common time fixed effects. So we assume that basically changes over time in units outcomes absent treatment are common
Hey,
across all
Rachel.
units. Oh yeah, hey.
There's a couple questions in the chat
Oh
asking for an example of a more than two times period study. If you are able to give one, a couple
yeah,
people are
sure.
asking for that.
Yeah, I'm gonna show one of those in the example when we get just a couple of slides ahead. So if you don't mind, hang tight for just a second. We'll see when you might have more than two time periods, and what might be the advantage of having more than two time periods in your data. So hang tight, and I'll get there. Thanks, Elaine. Also, when you're using the two-way fixed effects modeling framework, it's common that folks use standard errors clustered at the unit level, which I'll show you how to do in code in a few minutes, just to account for the fact that measurements across time within a unit are usually not independent of one another. So the sort of key assumption that enables everything in difference and differences is parallel trends. And often results from difference and differences are critiqued in the literature if folks don't believe that the parallel trends assumption is plausible for a given study. So the parallel trends assumption is sort of considered to be a very strong assumption in most settings. And we can sort of equate the parallel trends assumption to an assumption of no unmeasured time varying confounding, which can often fail in extreme weather and health research, for instance, if, for instance, treated areas might have different seasonal health patterns than controls. And so those different seasonal health patterns might mean that even absent the treatment, treated units' outcomes post-treatment would have differed from controls in ways that aren't represented in the pre-treatment period. So, this sort of assessing the plausibility of this parallel trends assumption is considered really critical in any analysis that uses difference and differences or two-way fixed effects. Formal empirical assessment of the parallel trends assumption is not possible. You can't formally empirically assess parallel trends for the post-treatment period, which is of course when we need the parallel trends assumption. But if you do have multiple pre-treatment time periods, you can try to get a sense of whether parallel trends might be plausible by looking at whether the trends in treated and control units were parallel prior to treatment. So this is often called parallel pre-treatment trends. And parallel pre-treatment trends provide sort of a good basis of plausibility for the parallel trends assumption post-treatment, but they don't formally validate it. So if you see that the trends in treated and controls were parallel prior to treatment, that's a good indicator that they might have stayed parallel following treatment, absent treatment, but it doesn't 100% guarantee it. So I'll show you in a few slides how you can sort of create a simple visual to visually assess parallel trends in the pre-treatment period when you have multiple pre-treatment periods of data. Ways that you can often improve the plausibility of the parallel trends assumption are to consider short post-treatment periods. So parallel trends becomes less and less plausible the longer post-treatment you try to estimate effects. And then, of course, like I said before, you can explicitly adjust in the regression models for time varying variables using that X term, and that also can help improve the plausibility of this assumption. So A couple other assumptions that are probably a little bit less forward in difference and differences, but are also important to assess when you're thinking through using this in extreme weather and health research. First, DID assumes what's called no anticipation, meaning that treatment shouldn't have any effect on outcomes before the treatment itself actually occurs. And so the way that this might be violated in extreme weather research is, if there's a forecasted extreme weather event coming and folks know about it several days in advance, the sort of anticipatory stress of knowing about the event approaching might increase adverse health outcomes even prior to treatment. And so that would violate this no anticipation assumption. Another sort of subtle underlying assumption of difference and differences is what's called no spillovers, meaning the impact of treatment on the treated units shouldn't spill over to affect the control units. And this type of spillover can happen in extreme weather contexts if, for instance, hospitals in the treated areas have such high demand that there's overflow into control areas. Can also happen because of migration out of treated areas following treatment, or things like supply chain disruptions that affect control counties as well. And finally, DID assumes what's called no multiple versions of treatment. So this can definitely be violated in extreme weather research, because we know that extreme weather exposures often really vary in intensity. So here we're sort of looking at exposed versus unexposed to a hurricane, for instance, but we know that places can be exposed at very different levels, and we're not really accounting for that. So these types of assumptions also have the potential to be violated, and are something that you can often perform some sensitivity analyses to try to look at how robust your results are to these types of assumptions. We can talk more about that if folks are interested at the end. First, I want to show a quick synthetic example. So again, this example is sort of motivated by a real event, Hurricane Michael, but none of the data that I'm using here are actually real. They're purely synthetic. So none of the effects that we see are real. They're things that we generated in the data. But I want to sort of show you a quick example just so that you are familiar with kind of the data structures and the basic commands in R that can be used to fit difference and differences in two-way fixed effect models. So let's suppose that we want to look at how Hurricane Michael affected all-cause mortality in counties that were exposed to it. So our units here are counties. Our treated counties are those that experienced sustained hurricane force winds from Hurricane Michael, and the controls are counties that are in the same region but not exposed. And then our outcome is monthly all-cause mortality in the county population. And we're going to be working with monthly mortality data for 24 months prior to exposure, and then extending into 24 months after the hurricane exposure. So this is a setting where we have multiple pre-treatment and post-treatment time points, 24 pre-treatment and 24 post-treatment. And we'll see that, again, particularly having a lot of pre-treatment time points allows us to kind of get a better empirical assessment of the plausibility of the parallel trends assumption. So I'll show that shortly. I'm not going to linger on R code since we don't have a lot of time. But here I'm just sort of simulating the synthetic treatment and outcome data. And the important thing to know about how I'm generating the data here is that I'm generating the data under the parallel trends assumption. So it is actually, the parallel trends assumption is actually met in these data by design. And the true treatment effect, the true effect of the hurricane that I'm generating in these data is that the hurricane increased mortality by 5 per 100,000 people. And then the fix est package in R is as kind of the workhorse that's going to be used to actually do the two-way fixed effects model estimation in this context. So I'm not going to linger on looking at the data too much, but I will note that this panel view package in R has a lot of nice functionalities to sort of make it really easy to make pretty plots of the trends that you see in your data. So with just a few lines of code, you can make a nice plot that shows sort of here in the colored lines, these are the trends in the treated units, and the gray lines behind them are the trends in the controls. And the dotted line here is the time of treatment. And then this FEOLS function is used to actually do the two-way fixed effects model estimation. And this, again, comes from that fix est package. And so you use the kind of standard formula language here for R, your outcome tilde, your treatment variable D that we talked about before. So this D variable tells us if a particular unit is treated at a particular time point. And then you use this kind of pipe notation here. And on the right-hand side of the pipe, you put your unit identifier and your time identifier. And so this will tell the model to include fixed effects for these units and these time points. And then note here that I'm also including this cluster equals county ID, which allows for clustered standard errors at the county level to account for potential non-independence of sort of multiple observations within a given county. And so your summary table that you get from this FEOLS function is quite similar to what you get from just your standard linear model function in R, except it does suppress the estimates of the fixed effects by default. You can access them if you need to, but it will by default just print your treatment effect estimate in the summary table here. And remember, I said that the true treatment effect in our data was 5. And we can see here that our DID estimate is recovering that treatment effect estimate. And then again, having all those pre-treatment periods allows us to empirically assess sort of the plausibility of parallel trends. Here we know, because we generated the data, that the data do follow parallel trends. But if we didn't know, we could make a plot like this, where here I've just plotted the average outcome in treated and control units at each pre-treatment time point. So from time 1 to 24. And we can see here that, of course, they're not perfectly parallel because there's noise in the data. But we can see that generally the lines here are for the treated and control units in the pre-treatment are pretty parallel, which would give us some confidence that the parallel trends assumption might be reasonable. And again, this is a big sort of reason that having at least several pre-treatment periods is advantageous, is to sort of make the case that parallel trends is plausible. I'm going to talk briefly about another quasi-experimental method that takes a little bit different approach to counterfactual estimation, called the synthetic control method. And this method has become insanely popular in the past 20 years or so. And one of the key advantages of the synthetic control method is that it assumes that you just have a single treated unit in your data. So difference and differences cannot be used when you just have one or very few treated units in your data. It requires that you have a lot of treated units. Synthetic control method can do counterfactual estimation and treatment effect estimation using just a single treated unit, and assuming that, as before, you have multiple control units. So this can be helpful if your data are sort of heavily aggregated across space, and maybe you only have aggregate outcome data for one one large treated unit. If you do have multiple treated units and you want to apply synthetic control method, you can still do that, but you'll just have to apply it separately for each of the multiple treated units. Our data structure with synthetic controls, it's still panel data, except now we're assuming we just have a single treated unit and then n-1 control units. And we've sort of measured their outcomes across time. And here we're going to assume that we have at least quite a few pre-treatment periods. Synthetic controls, unlike difference and differences, can't be used if we just have a single pre-treatment period. So we need quite a few pre-treatment periods to do counterfactual and treatment effect estimation here. Again, we need at least several controls and control units in the context of synthetic controls are sometimes referred to kind of collectively as the quote unquote donor pool units. So the key idea behind synthetic controls that's kind of analogous to the parallel trends assumption of difference and differences that allows us to do estimation of the counterfactual is that we're going to try to construct what's called a quote unquote synthetic control unit. That's just a weighted average of the control units. And the way that those weights are chosen to do the weighted averaging is to sort of best reproduce the pre-treatment trends in the treated unit. So we want our synthetic control, that's this weighted average of control units, to have pre-treatment trends in the outcome that mimic as closely as possible the pre-treatment trends in the treated unit. And then we take that synthetic control's outcomes in the post-treatment period and use those as our estimates of what would have happened with the treated unit absent the treatment. And we compare that to what we observed in the treated unit with the treatment to get our treatment effect estimate. So you can see that visualized in this little graphic here. So estimation of synthetic control method goes pretty much like what you would think from what I said on the previous slide. We're first just defining a synthetic control unit whose outcomes are a weighted average of the control outcomes at each time point. And we'll call the weights that are used in this weighted average the W stars. And these control unit weights are chosen using some mathematical optimization routines in order to get a synthetic control whose pre-treatment trends in the outcome match as closely as possible to those of the treated unit. So we're choosing the W's to maximize the match of the synthetic control outcomes in the pre-treatment period to those in the treated unit. And then we take those same W's, those same weights that we estimated using just the pre-treatment data. So we take those same weights and we compute the synthetic control outcomes using the weighted average of the same weighted average of the control outcomes in the post-treatment period. And we use that as our estimate of the counterfactual. So our estimate of what would have happened in the treated unit absent the treatment in the post-treatment period. And then we just subtract that estimated counterfactual from what we actually observed in the treated unit post-treatment to get our treatment effect estimate. And here we can actually estimate treatment effects at each individual post-treatment period, which is why I have the delta hat subscript T here, because we can get separate effect estimates for each treated period. I'm not going to talk in detail about how inference is done with synthetic control methods because it's a little bit complicated. But at a high level, I'll say that it's similar to what you might have seen called permutation tests or placebo tests in other literature. And so the high level idea behind how you would sort of compute a p-value with the synthetic control method is you would basically take each control unit and do a synthetic control method analysis, pretending that control unit is the treated unit, and then compute what we'll call quote unquote treatment effect estimates for that control unit. And then the distribution, we do that for all the control units, and then the distribution of those quote unquote treatment effect estimates that we've computed from the controls tells us about what the distribution of treatment effect estimates would look like if there really were no treatment effect. So under the sort of null hypothesis of no treatment effect. And then based on this distribution of treatment effect estimates under the null hypothesis, we assess how extreme or unlikely the treatment effect estimate that we got in the treated unit would be under the null hypothesis. So similar to permutation tests, if you've seen that before in other contexts. The limitation of these tests is that they're often really underpowered. So you need a lot of control units to even have the possibility of a significant p-value. So for instance, if you only have 7 control units in your data, the minimum p-value that you could possibly achieve with these types of tests is 0.12. So the minimum p-value that you could achieve is quote unquote not statistically significant using standard cutoffs. So again, these tests are often really underpowered. And so typically with synthetic controls, we rely less on sort of formal inference and more on just the estimates of the treatment effects that we get. So synthetic control method does not actually make the parallel trends assumption. It makes what's generally considered to be a slightly weaker assumption, which is good. It means that it's easier to be met typically in real data. Although it's a little bit harder to articulate. So the underlying assumption is a bit harder to understand than the parallel trends assumption. So here I'm sort of framing it as we're assuming that the synthetic control unit that we've constructed captures the influence of latent time-varying factors that drive treated unit outcomes absent treatment, so that drive the counterfactual outcomes. And we're assuming that the influence of those latent time-varying factors that drive the counterfactual outcomes don't change. The influence of those factors don't change in the post-treatment period. So again, this is generally considered a weaker assumption than parallel trends, although it's a bit more difficult to understand. Basically, the way that I often distill this for students and things like that is that synthetic controls is kind of allowing for unmeasured confounders whose values change over time, as long as their effects on treated and control units don't change in the post-treatment period. So you can have some, what we might call time-varying confounders, as long as the effects of those time-varying confounders on treated and control units stay the same in the pre-treatment and post-treatment period. And like the parallel trends assumption, this assumption is sort of fundamentally untestable, but we can assess its plausibility in our data by looking at sort of how closely the pre-treatment match is for the synthetic control and the treated unit. So I'll show you a little bit about how to do that here in a few slides. I just want to mention that the synthetic control method also makes the no anticipation and no spillover assumptions that we discussed for difference and differences. The only other big assumption that you need to be aware of or it's more of a condition than an assumption for synthetic control method is what's often called the convex hull condition, which says that the synthetic control weights are constrained to sum to 1. And so what this means in practice is that effectively, the synthetic control method can't extrapolate a synthetic control to have outcome values beyond the range of outcome values that are observed in the controls. And so this can cause problems if we have a situation like what's pictured here at the bottom, where the treated units pre-treatment outcomes are totally outside the range that's observed in the controls. If we have a situation like this, typically actually the synthetic control method will fail to converge and actually won't even be able to give you treatment effect estimates. I'm not going to go through the synthetic example here in a lot of detail because I see that we're running a little bit short on time. And also there's a lot of good documentation about how to implement the synthetic control method in R, in various vignettes online. So I'm not going to go through in detail the code, the data structure and the code here. Of course, you can reproduce it once you have the slides. But I definitely recommend if you're interested in using synthetic control method in your data, looking up the vignette for the I think it's called the synth package. Yeah, this synth package is sort of the key workhorse to estimate synthetic controls treatment effects. Um, what I do want to note is that the way that we typically assess whether the assumptions of synthetic control method are plausible is by sort of plotting what's often called a trajectory plot or a path plot. And these can be produced kind of automatically from some of the functions in the synth package. And basically, it's just showing the observed outcomes in the treated unit over time, and then the outcomes in the estimated outcomes for the synthetic control. And so what we want to see if the assumptions of synthetic controls are the synthetic control method are sort of plausible is sort of close alignment of the pre-treatment trends in the treated unit and the synthetic control. And so here you can see we have pretty decent sort of alignment. It looks like the synthetic control is generally capturing the upward trend in treated outcomes pre-treatment. And so this would generally be considered an indication that the sort of key assumptions of synthetic control method are plausible. You can also just make a plot of the difference in the observed and synthetic control outcome and look at whether the sort of pre-treatment differences in the treated and synthetic control are sort of randomly fluctuating about zero, which here looks like they basically are. So in sort of indicates that they're the assumptions of synthetic control method are likely plausible. I know we're very close to at time. So I am not going to talk, I think, about these modern extensions of DID and synthetic control methods in any detail. I'm just going to mention that it works out if you do some math, that both difference in differences and synthetic control methods are special cases of sort of using what we call in epidemiology latent factor models to estimate counterfactual outcomes. It's not obvious why that would be true just by looking at the formula for the latent factor model here. Some math is required to show it. But sort of this realization led to sort of modern extensions of difference and differences on synthetic control method that actually try to directly estimate the parameters of this latent factor model directly and use those parameter estimates to estimate counterfactual outcomes. And the reason that these factor model approaches to estimating counterfactual outcomes are sort of appealing is because they address some of the limitations of synthetic control method and difference in differences. So first, they allow for multiple treated units, unlike synthetic control method. They also allow for you to estimate effects on each treated unit separately rather than just average effects like difference in differences provides. And they also allow for the timing of treatment initiation to be staggered across units. So units can be treated at different times. And they generally have quite similar underlying assumptions to the synthetic control method, but they don't impose that convex hull condition that we talked about a few minutes ago. So these factor models are kind of experiencing a lot of popularity in recent years because they address some of the practical limitations of both differences and differences and synthetic control method, but they're considered to just be like a generalization of both. So I will, I think, stop here. I know we only have a few minutes left, but would be happy to take any questions. Elaine, I don't know if you have been following the questions in the chat and could sort of summarize or curate them to sort of maybe tell me what the most pressing concerns are.
Yeah, there's been a lot of conversation in the chat actually. And I feel like some of the questions are pretty detailed, so I don't know that I could accurately summarize them. If you want to take a look at the ones that have been submitted in the chat.
Sure. Yeah, likely won't be able to get to all of these, unfortunately, but happy to continue the conversation in future cafe events. So let's see. Hopefully some of these have been answered. This is a good question that's fairly straightforward to answer in a short time. Leah asks, does our outcome need to be continuous? The answer is no. There are sort of generalizations of all of these different methods that allow for non-continuous outcomes. So binary or count outcomes. You can use generalized linear models with two-way fixed effects, which is what Leah is asking. The challenge is that the parallel trends assumption becomes a little bit harder to conceptualize once you start working with these types of outcomes, because you're using sort of nonlinear link functions, and it sort of muddies the parallel assessment of the parallel trends assumption a little bit. So while in practice you can definitely go right in and use fixed effects models within a logistic regression or a Poisson regression, you can't sort of as easily assess the plausibility of the parallel trends assumption, because again, these models are using nonlinear link functions. Another good question is, do any of these methods work with case-only data or a case crossover design, such as ED visits from a single hospital? Typically, no. I would say case-only, case crossover types of designs can also have a sort of causal inference. You can also take a causal inference approach to estimation for those. But these types of methods, like difference in differences and synthetic control methods, generally aren't appropriate for case-only data. Let's see, maybe we have time for one more question before we wrap up. So let's see. Sorry, just need to read some of these. So Aaron asks, one major task for DID is to control for confounders that would compromise the parallel trends assumption. That's right. So the regression modeling framework for DID estimation is appealing because it can control for time varying covariates that would violate the sort of no unmeasured time varying confounding assumption of DID. And then he asks, can we use extended observations over the pre-treatment period to verify parallel trends? Yeah, okay. So I think we got to that one. We definitely should use the pre-treatment data to try to not verify, but assess plausibility of the parallel trends assumption. Okay, and I see that we're at time, so sorry I'm not gonna have a chance to get to all of the questions in the chat. You can feel free to follow up with us if there's anything burning. And you can also take a closer look at the slides once we post them. I also included some references at the end that might be really helpful for folks that are thinking about more advanced issues like spillover that I see in the chat. So thank you everybody for joining today and for being so engaged. Sorry I didn't get time to answer everybody's questions. Please stay tuned to our cafe listserv emails to where we'll post information about future webinars. Okay, I think I'm gonna stop share. Oh, thanks for the kind comments in the chat, everybody. Hope to see you at the next cafe webinar. Thanks.